About Alberto, thanks again, Alberto, for taking the time and for sharing your experience on detecting social relationship clusters using graphs. For those of you who do not know, Alberto is working with the IT department of CAIXABANK since 2007. He is an electronic engineer by education and also did a Master of Science in Artificial Intelligence, which I think is a great basis for all kinds of interesting work in this space. Alberto has been on the Big Data project at CAIXABANK since 2015, and in that context, he is involved in the digital transformation to convert CAIXABANK into a data-driven company. He is responsible for the analytical tools portfolio, so the Oracle BI Enterprise Edition, Oracle Analytics Server, the machine learning. The Graphs project is one of his successful projects. And he's also looking after the Big Data strategy. And with that, it is my great pleasure, Alberto, to welcome you, and the floor is all yours.
Thank you, Hans. Thank you for the presentation. And hello, everybody, and thanks, Oracle, for the opportunity to be here sharing with you our experience with graphs. What I wanted to share with you during this session, one moment, is a brief journey during our 6 last years to explain how has been our digital transformation project. And at what moment we decided that we need to add a graph database to our portfolio. I will show you how we implement the project from the point of view of the architecture, the data, format of the graph, and how we integrate it in the rest of the system of the bank, and how we can access and explore the graph. And finally, I will use a real use case that we are implementing to find social relations in our clients. I will explain later why we need this information with a real use case. And finally, I will comment just only 2 more graphs that we are using at this moment in CAIXABANK. Okay, so let's go with this short introduction, because if I were in Spain, I don't need to introduce CAIXABANK because it's one of the main banks in the country, but probably is not well known for most of you. So CAIXABANK is one of the biggest bank, and in terms of numbers, I have here some big numbers to have an idea. We have around 15 million of clients, or active clients. We have the largest physical branch network with more than 5,000 branches, the largest ATM network, and more than 9,000, and around of 50%, and these numbers are increasing every day, around 60%, they are accessing the bank through a digital channel, like a website or app. This is to have an idea of the volume of data that we can generate every day. Maybe this volume is not something big for your standards, but this is a big company in Spain. So we generate tons of data every day. Okay, and how Hans mentioned before, in 2014, we began our great digital transformation project to become a data-driven entity. It was 2012 when the big data wave arrived to Spain. And at that moment, we had our informational, but it was more from the point of view of a departmental repository. So we decided to join this big trend of the big data transformation, and thanks to the thanks to Oracle that was chosen our technology partner for this journey, not only for the infrastructure, but also for the vision and strategy of the project, we decided to begin our digital transformation to become to put the data in the center of the decision of the company. Okay, so the first years of this project, this journey, we were more involved in creating the repository. After 6 years, I can say that we are very proud of this repository because we have around 80% of the important data of the company. We have all the layers for security, ingestion, governance, and data quality, of course. So this is the main source for all the decision of the company for data science or any industrialization that need to access the data. These first years, we launched our first industrializations at that moment with R and using Oracle Data Integrator as for our ETL and SQL transformation. The next years, we were more involved in consolidating our portfolio of analytical tools because different than the traditional life cycle of developing applications in the informational world, let's say, our business users, they demand data and self-service tools because they want to be independent. For that, our portfolio of analytical tools is very important for the company. And all the time we are analyzing new solutions and adding to the portfolio like OBI, ClickSense, that allow business users and data science to do the job in a self-service way. Following years, we have been adding more state-of-the-art technologies like chatbots, artificial intelligence, real-time. And it was in 2019 that we were in a moment where the data were mature enough and the tools were also mature for the company, but was at that moment when we noticed that some of our processes were taking too long to finish. Especially we had some process for fraud detection that they do recursive searchings to find suspicious transfers between accounts, and they have to find in an iterative way different jumping from one account to another account to see to follow the money. And these processes over a database and based on SQL, they were not performing. At that moment, we decided that it was the moment to try the graph technology that I will explain in the next slide. The last years, we have been continue with adding more tools to the portfolio, new technologies like text, speech analytics, and at this moment we are defining the big data strategy business plan for the following years. Okay, so this is our journey during the last 6 years, and I wanted you to see that the graph technology is relatively new for us. So it was added to the company in 3 years ago. Okay. And why? As I mentioned, some of our processes were not finishing on time, and our fraud detection department asked us, I need something faster, I need to find relations, I need a tool to explore this graph, and it was the moment to try the graph database, because relational database, they are very good to keep data, but in a rigid structure, and they are not very efficient to find interconnections. The key points of the graph database, you have seen in the previous session, is that you have a flexible schema, so you can add different attributes for each node or each different edge, they give data and relationships the same importance. And this is this is the key when you have to find relation between data, not only the data. And what's more important, they allow you to run graph algorithms. This way you can use the out-of-the-box algorithms that are shipped with the graph server, or you can also develop your own algorithms. So to have an idea of when I say the improved scalability and performance, to have an idea of how faster it is, we did a very simple test. We find all the relations of a client with the contract, and then we find people that is related to contract. So two levels of relation. In our Exadata with SQL takes around 1 minute, and with graphs 10 milliseconds. So we are talking about, in our case, around 6 times faster to do these types of recursive searching. This is because they scale in a linear way, different than the relational database. And also you get the PGQL language that for this type of exploration, when you try to find relations, is much simpler to code. For example, this example, if you want to do it with SQL, maybe you have to code like 2 pages of code, but only 5 lines with PGQL. So this is because they are oriented to analyze relationships. And this is the big advantage of this technology. Well, how was our project? This is the big picture of the infrastructure that we deployed. And here, if we go from left to right, we have three layers. This is our repository. This is a graph server, and this is the integration with other tools at CAIXABANK. So here is where we have the data, our main repository. The data is modeled from the point of view of an informational use. I mean, as a star or snowflake tables. So the data must be transformed into a format that the graph server can understand. So with ETL and ODI processes, we search around the tables, and we prepare in a node and arrays format the information that we want to load in the graph. This is a process that we run every day, and during the night we load the graph. Okay. Then the graph is loaded in memory and is ready to use. You can query the graph using PGQL. Okay, and there are 3 ways to integrate with this graph. We have a visual interface for discovery, to navigate into the graph, to make some hypotheses, to validate some hypotheses. And we have a batch integration. This is to perform massive shared searching. And we have also integration through API for a near real-time integration. So we offer these 3 types of integration with the graph at this moment. If we look at the infrastructure, in our case, the graph server runs in a BDA appliance. This is because at that moment, because of the cost of the license, it was cheaper for us to install in a BDA with 6 nodes than installing in our Exadata infrastructure. But as was mentioned in the previous session, this has changed. The license is totally different now. So probably at this moment, we will do a different approach. So we have 6 nodes. At this moment, we are using three nodes. And the main graph the most important graph that we have, and I am going to show you now, is quite big. It's like 1.5 terabytes in memory. Okay, I am going to show you how is this graph. This graph was created because of the use case of the fraud detection. So the number of nodes and the arises that we have been including to this graph is because of the requirements of this department. So here you can find information, of course, about clients. We have 42 millions of records in this table. Only 15 million of active clients, but we have much more information in our informational from prospecting, clients, and so on. So we have around 42 millions of clients. We have contracts of these clients and the relation. We have the telephones, we have the address, the ATMs, credit cards, and purchases, withdrawal, wire transfer, because this information was necessary for the fraud detection. What we are going to see later is to find social communities. We are using this graph, but if in case we need a new information that is not included in the graph, it's very easy to add new nodes or to add new arises to this graph. Okay, to have an idea, we have here around 400 million of nodes and 2,000 million of edges. It's quite big graph with historical data of 2 months of money transfer and 6 months of credit card transaction. So this is our big graph and is used by 25 business clients, internal clients, to perform searches and to find suspicious activity. Okay. About the attributes, the same. One of the key points of the graph is that you can add flexible attributes to different nodes or arises. So the attributes that you can find in this graph are because the fraud department need for the job, like purpose of the transfer, amount, ID of the client, telephone, and so on. So all the necessary information that they need to filter and to find a suspicious activity. Okay. Well, and finally, I want to show you 3 ways that we have to use the graph that I mentioned in the previous slide. We have a browser for both for technical and for business users. Technical users, they can write the PGQL query, and then they visualize the graph, and then double click in the nodes or arises, they can continue navigating. This is more for first discovery. Let's say they have a hypothesis that they want to validate, so they search a client, they look the contract, they look the address, and they are here working until they find a pattern. The same for business users or analysts, but because they don't know PGQL, they can use a friendly interface for filtering. Okay. Once they have validated the hypothesis, we have a massive analysis in batch mode. So they can set a list of, for example, telephones, numbers, and they can define that they want to find the shortest path between them, or they want to execute a query to find some patterns, to find hidden relations between accounts. So this is a massive analysis that we perform once the analysts, they have found something that they want to investigate. And real-time analysis, we use only for some specific transactions that we want to analyze in real time, but it's very limited use at this moment. Okay, so we have seen the architecture of our solution from the point of view of the graph project. Okay, and now what I'm going to share with you is the use case. The idea of this project is to enrich and complete lack of information, like income, risk rating, of some of our clients based on their social relationships with other clients that we know better. In other words, tell me how you go with, and I will tell you who you are. This is a project sponsored by our Business Intelligence Department. Business Intelligence Department is the department that they do customer profiling to increase sales. They have to target the appropriate client with the appropriate campaign. This is what they do, and they develop machine learning algorithms to select the best campaign for each client. But they have a problem. The problem is that they don't have the same data for all the clients. If we have a client that is very active with us and interacts a lot with us, maybe we know very well. We know the income, we know the risk, we know the interests, but with other clients that they don't interact so often, we don't have so much information. So the idea behind this project is that if we can find social communities of clients, probably we can infer information from one client to another's, because probably they have similar interests, they have similar income, they have similar, they would like to buy similar products. Okay, so this is the idea of the project. I don't know how it is in your country, but in Spain, banks, they sell everything. They don't sell only a financial product. We sell telephones, we sell computers, we sell cars, houses, everything that you can imagine. So it's important to know what to offer to the right client. Okay. So this is the three parts of the client. We will use graph to identify communities. We will label that community, and that means that we will identify the profile of this community. So this way we can enrich data that we don't have, and then we can use this data for the model, machine learning models. Okay, so how we are going to identify these social relations? Our business department, intelligence department, they decide that we have three main sources that can identify, that could be used to identify these relations. One is credit card payments at the same time, same place. That means that if you go with someone to the same place and pay at the same times, and this place is a bar, restaurant, cinema, or let's say social place, probably you have a connection. I mean, your friends is your friend, is your colleague, but you have a relation. Okay, so we are considering 12 months of credit card purchases, and we are filtering only for this type of business, restaurants, bars, and cinemas and leisure places. And we are not using those connections that they don't match a minimum of days or different places. So this way we can create a connection between clients based on credit card payments. The second source that we can use is the money transfers, but not all money transfers, those only with a social purpose, like okay, this is for the gift, this is for the holidays, or this is for a family event. So if we can identify this type of money transfers with this social purpose, we can also set a link with a social link with these two clients. And Bizum Payments is a very popular app in Spain. It's a money transfer. It's not more than a money transfer, but it's an app that is very popular for friends. When you go to a restaurant with some friends and you don't have cash, your friend pay the bill and you send your part to your friend using Bizum. So Bizum, any transfer or payment with Bizum means that there is a relation, more or less, because very common between friends. So these three sources will be used to create the social graph. If we do a preliminary analysis of what we are going to find, we can see that 30% of the clients, about 5 million, they are linked with one or more source of data. Okay, the most important source is money transfer. It's around 5 million clients. They have a link with a money transfer, Bizum, or credit card payments. So this is the preliminary analysis of the data. Well, once we have defined the purpose of the project, we have defined the business rules that we want to use to identify a link, and we have the data. The following point is to create the graph. And here we have two different approaches. In this case, the first approach is when if you have a previous graph, then you can create a subgraph based on this already created graph. It's our case. We have, as I explained in the previous slides, we have this main graph created for the fraud department. Okay, to create a graph is not easy. I mean, in terms of computational cost, you have to create your ETL, you have to search your data in your repository, you have to transfer from tables to node and arrays format, you have to put in an appropriate structure to be understood by graph server. So this is a hard job. So if we can reuse, it's a good strategy for us. So if we have this graph in Exadata, what can we do is to create a subgraph when loading. We can apply some filters. So we will apply the filters that I mentioned before to filter only some types of payments, to filter only some type of transfers, and only Bizum transfers. So this way, I have a memory, a graph with the similar structure than the original graph, but with less nodes, because I am not using ATM, I am not using address, I am not using telephone, and only the information that I need. Okay, so to have an idea, from 400 millions, I can reduce to 18 millions, and from 2,000 millions to 380 millions. So this is the correct strategy, if I can say that way, if you have a previous graph with the necessary information. That is our case. Okay, so we have the social graph with similar structure than the original graph, but with less information. Another strategy will be to create the graph from scratch. Imagine that you don't have this big graph and you have to create from your data, from your raw data. In this case, what you can do is to create a smaller graph. You don't need to create a connection between clients through the node contract. you can create a link directly. So if you don't have a previous graph and you have to create from scratch, you can apply these business rules to your data when creating your tables. And then when you load your graph, you will have something smaller and simpler like this, because you only need connection between clients, and you have 3 types of connection. This is another alternative if you don't have a graph. Okay. Anyway, if you have this graph or this graph, the next step is to find the algorithm to do the clusters, to find the clusters. Okay. And here, our business intelligence department, they compare some algorithms because they were searching an algorithm to find overlapping communities. This was one of the requirements because one client not only belong to one community, probably belong to more than one community. This is because we need an algorithm that can find overlapping communities, and also performance was important. For that, they decide that this algorithm, the speak, listen, propagation algorithm, was the winner. What happened is that this is not a native algorithm in Graph Server. It's not one of the algorithms included with the installation. We have, as a native algorithm, label propagation algorithm, the LPA. So what can we do is a custom algorithm based on this native algorithm. This is something that allows to expand the functionality of the algorithm, adding this new algorithm. Okay. The way it works, I'm not expert in this type of algorithms, but the way it works to find the community is that in a recursive way, you set one of the nodes as a listener and the rest as a speaker. And the speaker, they propagate the label. Each node has a label, let's say ID or letter or whatever you want to propagate. And after some iterations, the label of the neighbors has been propagated to the other neighbors. Okay, so this is first iteration, for example, and you run this like 20, 30 iterations, and at the end you can identify communities sharing the same label. This is the idea behind this algorithm. So running the algorithm, we can identify the communities. In this case, for example, we have a big community with nodes sharing the A. We have a smaller community sharing the B letter, and we have a node alone in a community. Okay, so after finishing this process and removing those communities with less than 2 clients, because we don't consider that they are relevant, so communities at least must include 3 or more clients. We have identified that there are around 3 million of clients belonging to a community. We have identified around 6 million of communities. On average, 4.4 clients per community, and one client belongs to more or less 9 communities, and average friends, total number of friends of 13. So these are the numbers that we have found after creating the social graph, running the community algorithms, and analyzing the results of the process. So this is the output of the process. And what more we can do with this? Then we can label the community and use this data to infer data of the clients that we don't know. For example, imagine that we have found a community of superheroes, And these are the characteristics of the community. With the average age 35, they have income around 75 per year. They use credit card 10%, they use debit card 40%. So we can identify the characteristics, the profile of the community. And then when we analyze a single client into this community, for example, Captain America, we don't know if Captain America is using credit card or debit card. We don't know exactly, but we can infer because of the rest of the people on the community they are using. So in this way, for example, 80% of the people on this community, they have a mobile phone iPhone. So we can run a campaign offering Captain America the latest model of iPhone. Maybe he's using Android, but if all of the friends are using iPhone, probably wants to change to an iPhone. This is the idea, okay? Or he is using, we don't know the financial investment habits, but we know that people in the same community, they like variable rent. So we can offer some risky products to this client that we don't know very well, okay? So this is the idea behind the whole project. Find a social graph according to three main sources, apply and community algorithms, label the community, and propagate this information to the clients that we don't know, to run our machine learning models to offer some products. So this is the whole process that thanks to Graph, we can achieve and detect this community, okay? So this was the main idea that I wanted to share with you. And in my last slide, I just wanted to show you two more use cases that we have at this moment. One is the fraud detection process that I have been mentioned during my presentation. This was our first use case, and the main graph was created to give support to this case. And the idea here is to identify mule bank accounts. Mule bank accounts are bank accounts, not regular bank accounts, that the hackers, they use to move the money once they steal the money from one account. Then they have to move to different accounts for money laundering. This way, the money goes through accounts that they are not fraudulent. They are normal clients. So they are doing money laundering, and at the same time they are adding complexity to track the money. So they create, before they attack the client, they create a structure of mule accounts inside the bank, and then use, because they need this to move the money inside the bank before they can go to an ATM or transfer to another bank. So detecting this structure in advance is very important to prevent, to predict what is going to happen. And only with Graph we can see relations between these accounts, because they usually share a telephone, or they share an address, or they share something that we can identify hidden patterns in this structure. Okay, and the last use case that we are working is predicting risk propagation between interacting firms. Imagine that we have a client and we have some dealers, okay? in this case, this is the main dealer of this client. And this client has some cash flow problems. If this client doesn't pay the bills, the other company that depends 80% of this money will have problems, and so on. This client that works in this company will have problems probably, and this other company that also depends of the bills of this company. So we can find a cash flow dependency between companies, and we can predict the risk of failure of these companies once we detect a company that has cash flow problems. So this was what I wanted to share with you today. I hope you have found interesting my presentation, and thank you for your time, and any question, I'm here.
Perfect. Thank you so much, Alberto. I found that very fascinating. Thank you for all the insight into how you do your analysis and how you set up the entire project and so forth. We have a few questions, and anybody who wants to ask questions, do please stick them into the Q&A box. That's the best way of reaching us. So clearly, this presentation has sparked some interest. First question was on the fraud detection, actually. How many different fraud patterns your team detected? I mean, I guess this is an ongoing process, right? I guess you're continuously finding more or new patterns, but just to give a rough idea, Christoph was asking how many patterns did you already identify? Can you expand on that?
Yes, there are many types of fraud, but what we know that most of the fraud, they have in common three actors or 3 points. We need a hacker, we need a client, victim, and we need the intermediary. So we can't act against the hacker because the hacker attacks the client. So it's nothing that we can do here more than alert our clients, please do not give your PIN account to anybody, blah, blah, blah. But we cannot attack, we cannot do anything here. So we have to act here. And there are many different attacks, but as I told you, the way that the intermediary they behave, the profile of the intermediary, usually low income, they have low income profile, but they receive high quantity of money. They have something in common like telephone, or they share an address with someone that was suspicious in the past. So we can attack the intermediary network, not the hacker, and because we cannot do anything here.
Okay, interesting. Okay, thanks a lot. I hope that answers the question. Then Sahil was asking, or is coming back to your near real-time use case, and was asking whether you could explain a little more about that use case. I think that would also be a good opportunity to look at your performance requirements, because that was one of the key reasons for you to move to a graph database in the first place. So the question was, can you explain a little more in detail how the real-time use case works?
Well, this is what we are doing here. We have a very small graph with only some type of wire transfers, and this is this graph is in the middle of a process of the wire transfer transaction. It's not blocking the transaction. It's just alerting on real time or near real time that something is suspicious. But we are not still at that moment that we can put in the middle of the process and stop the transactions, because we don't feel still mature enough to do it. Okay, so it's real time from the point of view that when the wire transfer is sent, we call this graph through an API, and we receive the answer in real time, but only to fire an alert, not to stop the transaction.
I see.
And it's
Okay.
a smaller version of the graph because we need to be faster. Okay.
Yeah, no, I can imagine. I mean, clearly you cannot hold up all the transactions while trying to do the analysis. Thanks for the answer to that one. Quick comment from my side to Sahil. If you want to look at real-time use cases, you may want to have a look at what our customer PaySafe is doing. Feel free to drop a note to me in the Slack workspace, then I can point you to materials which PaySafe have presented earlier in the year at the conference. So next question was on algorithms. I mean, it's actually funny. We have like 50, 60 algorithms as part of the kit, and then it just does not include the one which you need. Now, Swati is asking, what graph algorithms do you currently use, Alberto? It's probably quite a few, is it? Or can you expand on that?
Yes, I'm not sure, but we are using the shortest path algorithm to find this suspicious relation between these mule accounts. I'm quite sure that we are using this shortest path algorithm, and I'm not sure. And once more, but I can't remember at this moment.
Okay, so maybe we can take that question also to the Slack workspace, and then we can follow up later if need be. Then I have another question on the community detection, which you did. Jasvinder is mentioning that looking at an average community of 4.4, that looks a bit like you had the size of an average family. So his question is, did you match the results of your analysis with other information you have, maybe about families, for example? Did you have can you find out if there are family relationships anyway, and then maybe filter out those because they are not relevant, or maybe they are particularly relevant? Can you maybe explain a little bit about the communities specifically, with the families and possible other information that you already have anyway?
Yeah, we have another project, similar project than this one, that we call a family graph. So because we can identify family by the address, if they live in the same address,
Place.
or if they share the same family name. But it's not obvious to identify family clusters. It's not obvious if you don't have that information. So we have another project, similar project than this, to identify family clusters. In this case, we have been using only these social relations to find these social clusters, but we don't have delete or apply any filter to delete if it's the wife, or if it's a family relation more than a social relation. So we have only used these three sources of information because we rely that with these sources will be more probably to find social interactions than family interactions.
Interesting. Okay, perfect. Alberto, I'm a bit conscious of time because we are 5 minutes over. That gives us still 10 minutes for the break, but I think
Thank you.
At this point, we should slowly come to a close. So thank you very, very much again for spending time on that. That was a very interesting session from my perspective. Hope to hear more at some other future webcast maybe. So thanks a lot again. For anybody who still wants to ask questions or interact with us, as I said, feel free to move over to the Slack workspace. With that, let me just quickly share